Hello, everyone, and welcome to the In Conversation series, a series exploring the makings of our exhibitions. In this case, we're talking about Deepfakes Art and Its Double, an exhibition curated by lead curator and director Professor Sarah Kenderdine at EPFL Pavilions Amplifier for Art, Science and Society at the Swiss Federal Institute of Technology, EPFL Lausanne, an exhibition which has actually been extended until May 1st, 2022. My name is Monica Antohi, Communications Lead with EPFL Pavilions, and today we're welcoming Pedro Santos, head of Competence Center Cultural Heritage Digitization at Fraunhofer IGD, and Matevz Domajnko at R&D Engineer and our 3D Digitization Expert at Fraunhofer IGD. Today we're discussing their project with us, their project that we're actually hosting within Deepfakes Art and Its Double, which is called CultArm 3D, which is a 3D photogrammetric robotic scanner, replica object, and monitor, all of it an installation that is, again, part of the exhibition. So hello, Pedro and Mateusz, and welcome to the In Conversation series.
Hi, Monica. Thanks
Hello,
for having us.
Absolutely. Again, it's the end of the year, and we're trying to actually make sure that we're exposing our audience to what you're doing, to the amazing work that you're doing with this scanner. So before we actually get to the scanner, before we actually get to what it's actually doing and how amazing an opportunity this is for the museum world, for the art world, let's give them a bit of a background into who Pedro Santos is and Mateusz Domajnko is, and how you guys got together and what brought you to build this incredible machine. So please walk us a little bit, give us a little bit of background into how did you get here? Because you started as a computer scientist. So what is that about? Like, how did you get from that to this?
Yeah, exactly. So thanks for having us at your Christmas edition, so to say. So yes, my background. So I'm around for a long time now. I've been almost 20 years with Fraunhofer Institute for Computer Graphics in Darmstadt, Germany. And I started out as a computer scientist. So this is what I did. My background is computer science. But first I started out in the Department of Industrial Applications. And industrial applications, well, we have a long-standing tradition of working with the automobile industry, and we did a lot of things for them, especially for the early stages of product design. We worked on the first immersive CAD modeling systems. So designers would stand in front of a power wall, basically, and create a car in midair, and it would be translated into the CAD representation for product engineers to refine. We did virtual wind tunnels, stuff like that, simulation applications, head-mounted displays, tracking technology. So all that stuff we did. And at some point in time, I became deputy head of industrial applications. And then, of course, you think, well, what do industrial applications have to do with cultural heritage? Because it seems to be so far off. But in fact, since we have this robotic arm at your exhibition, well, the connection is simple because in the automotive industry, of course, we were aware of scanning robots for a long time, but they were essentially dumb. And you had to teach them how a car seat looks like, and then they can scan 200 because they were used in quality assurance, for instance, and of course, manufacturing. But all in all, you always have to tell that thing what it has to do. And so for a car seat, it was about quality assurance, and then it can scan 200 that are the same. But then all of a sudden, we had a huge European project in cultural heritage with the usual suspects doing modeling, digitization, museums like the Louvre, Victoria and Albert Museum. And this was the time when also Microsoft started and Google started to scan books and everything that was 2D. And all of a sudden you had machines, you place a book inside, gets digitized in no time. And we thought, well, maybe the challenge in cultural heritage is there because you have lots of different objects. So back then, as I said, we would teach a robot how to scan a particular object. But here you have the difficulty or the challenge that you want to digitize entire collections of 3D objects, and they range from small objects to big objects, simple geometry, complex geometry, different materials, some of which you don't have the scanning technology to actually scan, like translucency, but we'll see that later. And so the challenge was there. And in parallel, we were coining the term of Industry 4.0. And Industry 4.0 stands for something like highly customized mass production at mass production prices. And it basically means that people actually want to have their products customized more and more, but they don't want to pay more for it. So you have to have the machining, the tooling, and all those systems in place that can actually do it. And of course, if you arrive with one of your items, I don't know, a simple object like a coffee cup, and you want something spray painted on it, then of course it would be nice if you had a device that simply scans it, has a model, and then you can actually control a printer or a spray painting robot or something that does what it needs to do, and you don't have to teach him how that thing looks like. And so this is how we arrived at the idea, well, couldn't we automate the process for 3D digitization of large collections and cultural heritage? And this is now where we are. So this is one of the outcomes after a couple of years. We started the department in 2013, and we've come a long way. And so now we're in your exhibition. And I guess I would just move over to Matevz to tell you where he comes from, what his background is, and how he joined us.
Awesome, Pedro. Thank you. And it's a huge path. It's a huge road that it's taken you to get here. Long, and it's quite interesting to see, you know, the thinking process, how you got led to do what you're doing right now. So welcome, Matevz. And let's talk a little about what brought you into this field. And you're not coming from computer science like Pedro is, right?
Exactly. So my background is in geodesy and geoinformatics. I studied it at University of Ljubljana, where I was later also involved in different research projects for 3D visualization of geodata, aerial scanning, remote sensing. And this is also a little bit the technical connection to what we are doing right now. So our system now is also based on close range photogrammetry, which is also a big part of geoinformatics. Anyway, so in 2014, there was also this interesting project in which Fraunhofer was involved. It's Marie Curie project for multidisciplinary, so digitization of cultural heritage project, initial training network. And this was kind of a nice opportunity also for me to join this project, and then Fraunhofer Institute. And I was this Marie Curie research fellow for 3 years. And afterwards, I started as a research and development engineer. That's also when we started developing the CultArm 3D system, which is at your exhibition right now.
So you're coming from scanning landscape in a way, right? Just the
big things.
I don't want to dumb it down that much, but you know, I want to like make it, you know, clear that you're scanning the points and kind of creating geodesy maps. So that's kind of what you guys are doing now. You're not scanning landscapes, you're scanning objects. So it's a fantastic blend of talent that came together to create this this machine. So okay, so you finally got together and you created this amazing machine. What does this machine do? I mean, we'll see it, and because I had the opportunity to speak with both of you at the exhibition, and we looked at the machine. But before we get to that part of the interview, give us a bit of info, like background on the machine. And yes, it's not quite the Microsoft scanning 200 seats machine. Not at all. That it's evolved fantastically since then. So what's the technology behind it? How what does it do? I'll let you talk.
Yeah, so I think first maybe we should also mention that, of course, when we started, there was no reference for how do you actually automate that process of digitizing everything, because in museum collections there is everything, so to say. And of course, we started out with the first thing that we did was a pipeline, a scanning pipeline, but it was very bulky. And then we thought, well, we could eventually reduce to a form factor that is more likely to be used by, for instance, the photographic departments of the museums and stuff like that. And so I think what makes us unique maybe is that we might have been the first to actually combine computer scientists, photographers, and mechatronic engineers in one team. Because typically computer scientists, they knew about photogrammetry and how to use it, but they didn't know about necessarily about robotics. And the same goes for photographers. They know about lighting, about cameras, about how to best light their objects, put them like on display. But they were kind of disjunct. And so I think what helped a lot was to actually bring all those competencies together to actually work on the first autonomous 3D scanning robots that produce repeatable high quality. And maybe I just hand over to Matevz. to tell you a bit about our robot then.
Yeah, so this robot, or you mentioned the pipeline, the whole pipeline. The second station of the pipeline was already the robotic arm, on which we actually then focused, and we thought, okay, like in terms of the size, objects that are present in cultural heritage field and so on, it's probably much better if we focus on a little bit smaller form factor, and we design like much smaller system, which is easy to transport to different locations and can really focus on the objects which anyone is scanning, and that's how we actually decided to design small robotic arm system, which is purely based on photogrammetry. So the system consists of, let's say, robotic arm, as we already mentioned, and also image sensors with specific lens and specific lighting, environment, which is everything together calibrated as capture configuration. Then we also have a turntable, and everything together is controlled by our software that we've written. And actually, we make sure that all parts of the object, the complete surface of the object can be automatically captured. So basically, an operator can only place the object on the turntable, and then the system will do everything for you. So it will detect where is the object, what is the shape and size of the object, and then it will try to scan it in different phases. It will continue scanning until there is still something unknown to the system, and it will try to capture enough data that it has, so enough data for calculation of high quality model at the end.
I mean, you have to imagine where we come from. Typically, right now, the scanning systems you find off the shelf. Now you have the hand scanners, for instance. Back then, we started out when there were structured light scanners on the tripod and the turntable. And the difficulties you would have with those systems were always that maybe you wouldn't scan everything, and maybe there would be holes, and you would have to fill them up manually. So manual work is always costly, I mean, in one way or another. And then, of course, what you fill up, you don't measure. So our aim was to really give you repeatable high quality, which means that with our system now, we can, for instance, guarantee that everything that the sensor sees, he will capture. So we can also give him performance criteria, like a minimum quality that he should achieve, by all means. And during the scanning, he keeps on planning additional poses to actually meet that requirement. So the idea was, and I think it's typical for the technology hype cycle, it all starts with a super great idea, and all the people, they want to have it, want to try it out, and the same was true for the hand scanners. So everybody all of a sudden thought, well, not that expensive as usual, so let's give it a try and we'll be able to scan our entire collections. But in the end, they saw the limitations of those systems. They have a legitimate application, of course, but if it's about to actually create scientifically suitable 3D models where you can guarantee a quality, then they reach that limit very quickly, because you might not be able to have color calibrated or color faithful reproductions. Then if it's a hand scanner, it depends on the person actually using it, how good the results will turn out today, tomorrow, and the day after. And then on the other side, of course, if it's about scanning hundreds of thousands of objects, I guess nobody really wants to do it by hand if they don't need to. Because also our let's say our conviction is also that what we developed should just be a tool. It should be as simple to use as the Xerox copy machine at the end of the corridor. You press the button and you know what you get. And because it's not about digitizing, it's actually about working with the outcome. So art historians, archaeologists, they should be able to virtually work with the outcome of what we do and use then virtual tools as they are used in the analog world to actually analyze their models, to compare models to each other, to superimpose, to measure things. So do their job, basically. So let's say our mission is to say we want to create a tool that is simple to use and you know what you get all the time.
Oh, and Pedro,
right?
I remember something very specific about it that you were mentioning earlier in our prior conversation. That you're trying to standardize the scanning. You're trying to standardize colors. You're trying to go to set up a level of quality that's kind of standardized across. Can you talk to us a little bit about that? I find that super fascinating and needed.
Yeah, so I think this is part of the whole game, so to say. The idea, for instance, that certain collections are spread over different museums. And if people now use different scanning systems and there is no minimum quality that they somehow adhere to, then in scientific terms, you would not be able to compare the results. Because you're comparing apples with beans, so to say, because you don't know let's say what standard was used to get the color right with the one system and the other system,
Exactly.
and so you cannot really compare results. And right now in the GLAM world, the archives are the most advanced, and they are adhering to standards like that ISO 19264-1 standard to do color calibrated digital photography. And then, of course, you can compare the results if you go by the book and really do it according to that standard. And this is where we want to get to in 3D as well. So we have been trying to port also standards from 2D to 3D as best as we can, or create de facto standards to actually enable people to actually use the results then for such purposes. And Matevz has been instrumental in actually working on this. So you can probably tell me more about what it means to actually pull it over to the 3D world.
So Matthew, huge job to go from 2D to 3D, huge job, especially in terms of standards. How are you managing that? What does that involve? What's the process?
Yeah, we have to first, of course, break down the whole process in 3D, and then we also have to understand how standardization in 2D works. So if we consider, let's say, a 3D model or an object which is 3D, and if we kind of break it down or slice it into very small pieces, the whole surface of the 3D model or 3D object, and then if we really slice it down into very small pieces, and then we can compare it to 2D parts, and then each of these parts would actually meet some specific standards in 2D, and then we try to, with this standard in 2D, we try to describe the complete surface of the object, and this is kind of the approach that we are trying to do here. So we are trying also to address separately geometry and then textures or colors of the whole object. And we try to break down complete surface of the object into small pieces, and then we try to standardize or define a little bit standard quality for geometry of the object, and then also colors and resolution of the textures of the model, which is applied or projected on top of the 3D model.
But it goes on basically because the scanning project itself. So once you scan an object, we already store the data in a way that you can reproduce the scan, so to say. So we store the raw data of the scan that we did. We store the high resolution models. We store the technical metadata like the lenses that we were using or the poses that were used to shoot images, because the whole system is geometrically calibrated. So we always know from where we are shooting an image. And of course, we also store the semantic metadata to the object that the curator might type in. And in this, for instance, in that direction, we go towards EDM standard, for instance. So we support the Europeana data model. So you could directly link our results in Europeana if you wanted to. Also, we try to store the raw data also in standard images that are lossless, so that you can actually be sure that you got everything. And yes, and then it goes on and on basically, because then also the process afterwards should go into that direction. That, for instance, you want to store data in CDOC CRM databases, so you have the mother of all ontologies to classify your data. We have just recently submitted a European proposal in which we want to actually, the idea is to go towards data enriching data, because we see that the curators will not be able to actually annotate all the thousands of objects that might come in and be digitized on their own, because it's too much stuff to do. And so one of the ideas is to also try to take a look at legacy databases and 3D-fy them, or search for attributes of already stored models, images, anything, so we can automatically find correlations between 3D models, 2D images, photographs, PDF documents, and then eventually give the curators a kind of expectation list that they only have to say, well, it's true, it's not true, it's correct, it's not correct. And so we backpropagate the results back into the legacy databases and enrich them with that information. So there are all those ideas that we're floating right now. Some of them we're pursuing as a department, and some of them, of course, we have to pursue with partners.
Yeah. It sounds like a tremendous amount of work that can be done for museums, for the curators. You're saving curators a lot of thinking process, a lot of, how am I going to do this? They don't have the expertise. A lot of the curators come from the art world. We're not coming from necessarily from the technical world. How are we going to even start looking, start scanning this? So your scanner, your machine, because it's not just the scanner, it's the whole thing, right? It seems like it's reducing a tremendous amount of work for the museum world, because a lot of museums are trying to save some of this, some of these artworks from degeneration, and by digitizing them, we can preserve them for we can show them, we can preserve them for further generations. But it's specifically the amount of work that you're saving, to me, that's kind of what resonates, because we know how much work it's involved in running a museum, running a collection. So what is, like, how much of that are you saving? Because I think I know, but talk to us a little bit about that.
Maybe I explain first how it's typically done in 3D digitization. So if we consider how many people are necessary and how much expertise is necessary to do complete workflow, let's say from planning the project all the way to having 3D models on the web, for example. So it starts usually with planning and inspecting the collection or museum objects, and then also deciding together with a scanning expert what kind of technology will be used, from, let's say, photogrammetry, laser scanning, and also how everything will be acquired. Then museum curator typically would have to place or position the object in a safe way so that the scanning operator could move around the object, could capture all kinds of data, would make sure that everything is really captured with the scanning device. It can be handheld scanner, it can be laser scanner. There are different approaches, or also different cameras for photogrammetric acquisition. And then here it's also maybe already the first automation, the first important point that we are addressing. It's also automation of this capturing process, that so the system will always capture it in the same way. So if you have different scanning experts, every time you will get different kinds of results. So let's say, or even the same scanning expert, if it scans it in one day or another day, it might be, again, different result. So this is, let's say, the acquisition. And then when all the data is captured, the data goes into the processing workflow. So there are different approaches how to process the data. Maybe the raw data needs to be processed, or also some images need to be pre-processed and so on. And everything needs to be prepared for calculations. Typically, I mean, there are different approaches. For example, if we talk about photogrammetric or image-based 3D reconstruction process, this also takes quite some time. It's mostly it's automatic process. And then what operator would typically get out, it's a high resolution 3D model. That model, where many times needs to be then cleaned further. There is like some noise on the surface, depends also a little bit on the material. There are some holes, what Pedro already mentioned before. These holes need to be closed, and here many times you need also another expert, so-called 3D artist, that would actually work on this model, would close the holes, would clean some parts, and so on. And then this model needs to be further optimized for a specific use case. For example, if you want to put it on the web, it needs to be converted, or it needs to be optimized for web viewing. The model can be prepared for augmented reality, or for some video can be prepared, and so on. And this is like, let's say, then the 3D artist or another expert prepares this model for final use. And what we
wait, hold on. How many people do we have at this point that have that were working on this?
It's quite a lot of manual work.
Quite a lot of them. Okay, let's continue, because we're not done apparently.
Yeah, so typically now we are already at the end, and I mean, this can be, of course, also the same person that would have expertise in different fields.
But let's say, yes.
But that's not the case, right? That's not
probably
the case in real life.
So yeah, not always. So you would need. What is always necessary is, of course, museum curator that can safely place and handle the object. And then in terms of the expertise, it's, of course, the planning of the whole digitization workflow. Then it's someone who needs to, or who knows how to capture the data, how to do scanning process. Then it's, let's say, data processing. Let's say pre-processing and processing, and then when we have the 3D models, someone needs to know how to deal with the 3D data. These are usually 3D artists, and usually they also know how to prepare and optimize the models for final use. And we are trying to kind of address the whole workflow, so that you would need only museum curator or someone who can handle and place the object safely, and then can be the same person who just starts the process, or it's another maybe student or another operator who just chooses the actually the system allows you to choose the quality that you want to achieve at the end. And you can choose also what kind of models you want to have, for example, for what kind of purposes you want to get the 3D assets, for example, for web viewing and so on. And then the system will try to do everything completely automatically. So from capturing the data, capturing the data, collecting the data, processing, optimizing, and then at the end, the system can deliver different assets from video renders, web-ready models for augmented reality, and so on.
And 3D printing models as well,
and
because
we're
that's when we
working on
have
3D
it.
printing as well. So we also have a department at our place. They are focusing on 3D printing. But there is some add-on. 3D printed models are a bit more complicated because sometimes you have to remove non-manifolds, technical stuff. But we're working on that as well, because then we would go full circle. So from real to virtual and back to real. And our printing department is actually working on the ultimate printer drivers for photopolymer printers like inkjets in 3D, basically, that also give you the color faithfulness of the original and mimic the light transport above the surface, below the surface, and stuff like that. So, and we already have a couple of projects in which we tried out the full pipeline, and it seems to yield good results. So
one of them is in our exhibition.
Yeah, exactly. So if you take a look at the mask, the samurai mask from the Samurai Art Museum in Berlin, one of our cooperation partners, that mask, we printed it out exactly with that printing technology. And we would also mention the two other partners. We have, of course, a cooperation with Phase One, the camera manufacturer, and Stratasys, the 3D printer manufacturers, and so they all helped in actually creating this exhibition and actually showing the full circle, like from the real mask to the virtual mask back to a real mask that mimics the original one. And I think if you're like a meter away, you won't notice too much of a difference between the original and the printed one anymore. It's amazing.
A lot of people think that it's the same.
Actually, it should be the other way
original.
around, right? The original should be on the turntable and the replica should be on the stand. But of course, we cannot just let the original be there. So it's scanning the printed mask, right?
Right.
But you get the idea.
Absolutely. And the fascinating part about this mask, well, besides the fact that it's a beautiful mask and it's kind of creepy, but it's absolutely creepy in a beautiful way. It's got so many surfaces and so many textures, and it's a metal with fabric with there's a lot of worked metal. There's a lot of chains and fabrics, and we'll show it. We'll be playing that into part of the interview next, and then we'll be showing that. But scanning that, because if we're going into scanning museum objects, there's all kinds of materials that need to be scanned, but in this case specifically, you're talking about reflective materials. You're talking about materials that absorb light as well, like is in the fabric. So how difficult is that to scan with this machine?
I guess this is, again, one of the points. Matevz, go ahead.
So with the system, we try to really make sure that it's possible to scan as many materials as possible. Typically in 3D scanning, there are some materials which are very challenging. For example, if we talk about transparency, shiny objects, and so on. With the system, we try to really optimize lighting environment or the ring light in a way that we can already tackle some of these challenges. So reflective surfaces are typically not a problem. We try to do some lighting tricks from polarization, using specific LED lights and so on. And the system can already very efficiently can capture also reflective objects or reflective surfaces. So for example, in this mask, the main part of the mask is metal, shiny metal, and this was not a problem at all for the system. Perhaps if there would be very transparent part of the object, this could be a little bit tricky. It's still tricky for all kind of known technologies. But then also if we have different kind of materials, which is the case with this mask, for example, some surfaces which are very that absorb the light, some reflect the light, and so on. This is not a problem because the system can detect all kind of surfaces, and it actually follows it always in an optimal way, and it really tries to capture all the details on the surface of the object.
Yeah. So currently the limitations would be something like translucent materials, maybe like glass. So this is something we cannot yet scan. So we also don't want to promise the blue out of the sky, but it's we're trying to narrow the gap of what is not yet possible, right? So we're basically closing in on the 100% if possible. But of course, because there are so many different objects and materials, there's always some limiting factor, but we're really narrowing the gap now. And so shiny surfaces aren't really a problem anymore. Translucency is still a problem, but also we already have scanned ivory objects, for instance, where you also have semi-translucent surfaces, and we have some light transport underneath the surface, and it worked out pretty well. So we're getting there. So that's an ongoing process. But yes, lots of challenging materials.
Awesome. So let's see a little bit of that interview that we did on site, and then we'll delve deeper into that from that point of view, and then we'll come back and continue.
Sure.
Pedro, we were talking about all of this, but I want to know how it actually works really quickly, and then we can go into the nitty-gritty, but let's just walk it over really quickly. So I'll let you do it.
So the system itself is composed of a robotic arm, a camera, a ring light, and a turntable, and that's the robot. So the robot is not just the arm, but it's the whole of the thing, for which we have calibration steps. They are push-button calibration steps, and for which we have then the scanning processes. And as my colleague will show to you later in more detail how the system works, you will see that it is suitable for technically non-proficient people to use. So the idea was to make it as simple as using the Xerox machine at the end of your corridor to actually get photocopies, to actually use this system as well and then get 3D models out of it, which are always of the same quality. And so when you look at the individual parts, you have a robotic arm that is compliant, which means we can stand right next to it. Nothing will happen to us. We can even stop it with our bare hands if need be. And the reason also to use such an arm is because it's pretty fail-safe. So as long as it has power, the brakes in the joints will be kept open. And if we have a power failure, it will just stay in position and nothing will happen ever to objects. We have different layers of safety, which my colleague will probably explain in more detail. We have a 100 megapixel camera, which is a very high resolution camera, to actually capture all the details of intricate objects as well. We have a ring light of our own build because we didn't find anything on the market that was suitable to us, and which also offers a homogeneous light spectrum, which is also important to do the color calibration right. And that's it basically. And the rest of it, I think I would just hand over to my colleague to explain to you.
Yes. So how does this work? How the machine works, and how is it actually improved upon the entire process of 3D scanning?
So we try to think a little bit how to automate the whole process, how to make it user-friendly. In the past we had lots of different projects, 3D digitization projects, where we try to use different technologies from structured light scanner, photogrammetry, laser scanning, and we try to learn what we can actually improve or what we can actually automate. So in this system here we try to really optimize all kinds of manual parts for processing, scanning, and so on, in order to get kind of easy to use or user-friendly system. How it typically works in 3D scanning or 3D digitization, you need, for example, a scanning operator that plans the whole digitization process. You need a curator that has to place the object safely in a specific way, also reposition it multiple times so that it's possible to kind of digitize it from different directions. Then all the data needs to be captured or organized together in order to start processing. For processing, there are also lots of different approaches. What comes out is typically a 3D model, which needs some post-processing or, for example, cleaning or closing the holes and so on. And for this, usually there are 3D artists that do this job, and then they can also optimize the models further, for example, to prepare virtual exhibitions or to prepare web-ready models or models for 3D printing and so on. What we try to do here is we try to address all of these steps in the whole workflow and to put it in one complete solution. So with this solution, you need only a curator that safely places the object or stabilizes the object on the turntable. We provide also different mounts and stands for nice placement of the objects, and then operator only needs to select required quality for digitization, and then it can start the process.
That's it.
That's it, and then the system will do the rest for you.
Show us this magic machine. Show us how this works.
We can start with one typical scan. This is kind of a little bit faster digitization process for the exhibition here. So now it is in the first phase where the system will try to detect what is the shape and size of the object. It captures images from different size of the different sites, and it will detect basic shape, basic size.
The
rough model. Basically, we will see also the rough model already, and this rough model will be used for precise digitization planning. So the system will then precisely plan all the images, all the captures, and it will continue as long as it can still capture some, or as long as there is some missing information.
So the system kind of does it itself. We don't have to plan the scan. We don't have to kind of create a rough model for it. It just does it itself.
Exactly. So everything is done in our software. We use some smart algorithms to actually detect the whole object, to do all the planning, and then it does everything on its own.
Fantastic. What kind of surfaces is it able to pick up on, and to what detail? Because we were talking about just a little earlier about how a digital artist would have to come in and kind of finish the model, right? Mm-hmm. Is that needed with this machine? What kind of jump, what kind of leap in technology is this machine providing, basically?
So there are actually two big benefits of this machine. One is already on the acquisition side, because the system really follows the whole surface of the object, all the details, everything what is actually visible also to a human eye. And then it really tries to capture all the data there. So typically or traditionally with operators, it always happens, or also it happened to us a few times when we did manual scanning. You always forget maybe specific detail, you're tired, or you forget one to scan or to acquire specific data of the object. And here, because everything is automated, the system of course continues and follows complete object as long as there is something visible. So this is one benefit on the acquisition side, and then all this data is actually processed together in automatic workflow so that we get already a complete model, complete in terms of geometry and in terms of the textures. So the quality that is achieved here in terms of geometry, it can go even below 20 micrometers in resolution, and then also texture resolution also is around, or the highest texture resolution is around 10 micrometers.
Right, so it looks like it's done the first part of the scan, and then we'll see the shape it just populated in there, and now it's going to start scanning details.
Exactly, so what we see here, it's already the first rough model. This it detected it in the first phase, and now it plans already the views for the precise acquisition, or for high quality scanning. We see also here on the screen that it's already projecting existing views, so already from the first phase it already projected some of the views on the model, and now as it's capturing, we see also in terms of the colors that it's also covering the whole object. So this is, for example, now the second phase, and these phases would continue as long as there would be something new to capture for the system.
Just one quick final question. How long does it actually take for, well, I know it's depending on the object itself, but for an object like this, with this kind of level of complexity, how long does it actually take to have it fully scanned, to be able to be reproduced in 3D or virtually?
So of course it depends also on the quality that we want to achieve. There is also, we have different scanning workflows, and for example we have quick mode, which would capture this object already with most of the details in, let's say, 10 to 15 minutes. This would be already a good model for, let's say, web presentations, for virtual reality, augmented reality, and so on. If we want to go with the highest quality, for example, for 3D documentation purposes, for scientific purposes and so on, then the scan would take, of course, a little bit more time. It would run probably in, let's say, 4 to 6 different phases, because it would try to capture all the small details also in highest possible resolution, and this can take also up to 45 minutes. But the best thing is that everything is absolutely automatic, so operator doesn't need to do anything, only selects, let's say, the quality for 3D documentation or highest possible quality, and the operator can have coffee or can, for example, focus on other work, or
can actually do some curator work.
or curate, exactly.
Go back to like proper work. But in terms of speed, it's phenomenal. It's super fast, and it's the fact that you're removing all of the errors that you're talking about when a 3D, like if I would go and start taking images of it, I'm going to miss some stuff. I'm going we're human, so that's where the 3D artist will come in and fix those issues. There's no need. There's no need for that. Everything is done. Everything is automated. It's a push of a button. You just set up the object, and it's good to go.
Exactly, that's the best part of the whole system, that you don't need the 3D artist, you don't need a skilled operator for scanning that needs to reposition everything, plan the whole scanning. So basically that's the best part, that the system does everything for you, and always it does with the repeatable high quality, which we are also now developing specific standards, so that it will also meet specific standards for quality standards.
Quality standards so basically it can be reproduced. So the qualities will be similar across multiple museums, multiple collections, multiple countries, if you think about it. So it's not a matter of, it's not going to change. Your outputs are not going to change in different countries. This is phenomenal. But what other applications do we have for a machine like this outside of museology, which that alone, it's going to be able to save, from my point of view, save a lot of cultural heritage objects, but it's got impact outside of that as well.
So what happens at the end is, like, we get, let's say, the typical output, or the first output is a high quality 3D model.
Yes.
We call it for 3D documentation. So it's really a model which has repeatable high quality, which means also that if without the system, for example, if one scanning expert would digitize one object, would be different quality, the result would be different than if someone else would try to scan the same object. The good part of the system is that the result, what will come out, or the output, will always be the same and always at the highest level. And this is, for example, the model for 3D documentation. And then this model is also automatically optimized further for different purposes. For example, we get out automatically model for virtual reality and augmented reality, so it can be directly used on your tablet, on your headset. Yeah. What also happens, we get also a model for the web, so you can put it directly online, and also the rendered video, which we see also behind us. Also, this is automatically produced based on all the data that is captured with the machine.
So we just heard Matevz give us an overview of what this incredible machine is doing, but what can museums do with it? What's the impact for culture? What's the impact for heritage preservation? How can museums benefit from this technology? We know how we're benefiting from it, but what else can we do with it? What can we do with it every day?
So I think we go along the 3 priorities. So the system needs to be safe, that's number 1. For all the objects that we place on that turntable. We want to give you repeatable high quality, which is super important to have scientific results. And then you can create all the byproducts using our reconstruction service that can actually calculate the web-ready models, or the 3D web models, that can actually do videos, as you see on the wall as well, and that can actually get you augmented reality scenes. So all those byproducts can be done next. And then the other thing is, it should be very simple to use. And as you could see, it's a push-button system. So it also means that you don't require technically proficient people to use it. You can actually have one operator overseeing 6 systems. Or the curator himself is he's just concerned about actually placing the objects on the table, taking them away, and everything else is push of a button. And it gives you repeatable high quality, and you don't have manual post-processing. So we don't want to promise you the blue out of the sky, but let's say that if for 90% of your collection everything can be done automatically and you don't require manual post-processing, it means you save that time, you don't have that work, you can rely on the quality that comes out, and you can actually do more in less time. And systems like these can run 24/7. So typically with manual work you have shifts, and so this will help immensely because you get the same quality all over the same collection. And then of course you can use all those 3D models for different new avenues of revenue, like doing hybrid exhibitions for instance, or also do concurrent research on the objects, because then you can ensure that they're all looking at the same thing. And so it goes. And also for merchandising purposes, you can then create variants to actually sell the most interesting parts to people. And for instance, one of the arms that we have out there is at the State Museum in Baden-Württemberg in Karlsruhe, and they have a new visitor concept where they engage more with the visitors coming, and they can actually set a date with one of the explainers to scan an object of the collection themselves. So just with a curator on location, and they can press the button and then see how the object is scanned, and then later on they can interact with the results in virtual worlds, on touch tables, wherever.
We're not talking about the 3D printed stuff, we're just talking about the virtual objects, which are phenomenally rendered. But we're also looking at the absolute quality of what we're scanning, and we're seeing the quality of the scans, basically, on object with such intense differential texture and shine and depth, and so we're not talking about one type of object. We're talking about pretty much everything that can be scanned. So yeah, in terms of impact for culture, it's a way of basically preserving culture for long term without,
yes, of course,
without touching, without degradation from.
So that's the number one goal of a system like this, is of course the preservation of the original objects in a digital way. It's not to replace them, of course, but to have a copy. I mean, you only have to look at the media, man-made disasters, natural disaster strike. Then right now we have one of the huge topics coming up is also restitution of objects, for instance, to their original locations, and maybe you want to actually keep a copy. That could be a digital copy. Or whenever you have new findings, maybe you cannot actually bring them back to your country, but have to stay there. And so you could digitize on location. So that's also one of the things or advantages of a system like this, that you can actually bring the system to the objects or vice versa, because it doesn't need too many resources. A regular socket, power socket in the wall will actually do the job, and you don't need anything else. So you can also create it and ship it anywhere you like. So this is, I think, the advantages that a regular person can actually use it and be sure of the quality and the results they get.
It's fantastic for anything that has to do with heritage, with cultural preservation. So in terms of what's next for what you're doing, what are the next steps?
Well, I mean, right now what you get is you get the shape and the appearance of an object. Of course, we're going to push it further, and we're going for things like multispectral definitely at one point in time, because there's much more information that you can get than meets the eye. But the first thing to get right is, of course, the level of automation, that you have a push-button system that gives you geometry right, that gives you color right, and then you can go for the next level, which is then maybe multispectral. You can go, for instance, for ultraviolet illumination that gives you the marks of a chisel on a wooden statue, so you can even infer how the artist, the technique of the artist that was used to actually create that piece of art. Infrared will give you information about the conservational state of an object, for instance. And then, of course, there is this overarching idea to go towards consolidated 3D models, to fuse this technology with CT scans, mass spectroscopy, everything, to create digital replicas on your screen. And actually also have the tools that you have in the real world, in the virtual world, on the screen, so you can work with the 3D objects as if they were on your table, and leave the originals as much as possible alone, and actually provide concurrent access to multiple people to work on the same object and compare it, measure it, simulate things. So from man-made objects to natural history objects, we see that there is quite a large demand for a system like this that can do it.
And one of the pivotal points from my point of view is the standardization of color and texture, and that sets the bar to a level that hasn't been seen before.
Exactly. So as Matevz said, we try to adhere to standards. So all the data that we store the metadata in EDM compatible format, which is the Europeana format. We are active in all those groups as well with the European Commission, with the Europeana Task Force, CultArm, digitization guidelines that came out from the Commission. We also contributed to them because we try to go towards standards, and the way to get standards is to go de facto standards and then move on. We try to transfer the ISO standard from 2D on color and digitization of 2D objects to 3D as much as possible to see if we can actually provide repeatable high quality. And as Matevz also explained, you can add additional scans or additional scan passes to an already existing project. We document everything with a timestamp so it's reproducible, and so it goes.
All right, so we just saw you guys talk about this machine on site. We saw how amazing it moves and how it scans and what it does. A little bit more, I don't want to say hands-on, but we were right there and we were watching it do its magic. What's the impact for the museum world? What's the impact for culture, and what's the impact for cultural heritage of this machine? And we saw how it can benefit museums because we see what it can do. But in terms of preserving cultural heritage and having something for the next generation, where do you think this mission fits?
Yeah, so currently, and also with the ongoing pandemic, it's well, not very nice, but it's somehow helping digitization. Because of course, what you see is that you're no longer actually busing school loads of kids to the museum because you can't. And so the museum artifacts have to come to the school classes, for instance. So this is one of the, let's say, the application areas of what we are doing are such that you can have actually the collection come to you. Or you do have collections spread over different museums, and not everybody has everything. But by doing hybrid collections or exhibiting hybrid collections, they could show all the collection to everybody. And that would be something. Or you have topics like restitution of objects by now. This is very, very contemporary problem that many museums are dealing with, and so they have to restitute objects, and then maybe they want to keep a high quality digital model to actually continue to do research. And also in the places that you used to dig out findings, you are no longer allowed to actually export them out of the country. So also in that, connected to that, our autonomous scanning system could be sent on location in a container ready to be used. Just push the button, you don't need to know anything about it, and you can scan objects right there on location and actually transfer the virtual model to a museum for further research. So this is all kind of application areas that we see. And then of course it simplifies the process of digitization and gives you repeatable high quality at the push of a button. So basically one person would be able to oversee 6 of those machines or 8 of those machines. So imagine the throughput that you can achieve because everything else is done automatically by your processing cluster. So that's where we're heading basically with this development.
Huge opportunity for expansion and bringing culture to more than just the museum goers like we're accustomed to at this point.
And that's yet another point, because there are other application areas. I mean, online auctions, for instance, or use them as props in edutainment, for edutainment purposes, for documentaries, even for games. Could also be serious games. So people actually, many of the school kids, they're used to walk to Disney World and to all those theme parks and exhibiting the latest in technology. And then how do you get them to go into a museum and actually appreciate their heritage? So you probably have to come up with similar technologies to make it attractive to them to actually interact with that sort of topic, right?
It sounds like a plan for the next generation of teachers, or the current generation of teachers, and bringing a bit more culture to the classroom, which is always a challenge, and it's always appreciated because, yes, as we know, culture kind of permeates everything that we do. But what's in stock for you guys next? You were talking about a little bit more about the 3D printing aspect of this project. What else is in stock for you guys? And maybe you want to take that conversation a bit deeper into the 3D printing.
So yeah, we are thinking a little bit how to expand also the system. The system, well, as it works right now, it's only let's say the base system on which we will add new technologies. So also new kinds of sensors, new methods that can do much more. So this is only the, let's say, the first system on which you can add different things, and then the smart algorithms which we developed for the system can use also other sensors and other technologies. More in details, probably we will not go at this point with what kind of sensors we are developing or what is also the idea for the future. But we can also comment a little bit what we are doing with 3D printing. So we are planning that the system can deliver already ready to use, ready to print models, which the next step is that also can be printed, the models that are delivered can be printed also as, let's say, perfect replicas where you see exactly which parts are shiny, maybe even translucent and so on. And this is, let's say, the next step in terms of replicas.
Exactly. In terms of, thank you, Matevz. In terms of deepfakes, this is the ultimate tool to create deepfakes and to create as close to real copies of, well, as close to the real, as close to the original, let's put it that way, scanned object as we can possibly get to. This doesn't feel like an interview. This felt like a gift to the curator world and to the art world. So I wanted to actually thank you both for your time and for the conversation and for the overview of this CultArm 3D amazing project that you both working on, and happy holidays from Lausanne for you guys. Thank you so much again, Pedro and Matevz. Any closing thoughts on your side?
Oh, well, I mean, from our side, we'd like to wish everybody a Merry Christmas as well, in a pandemic, as well as you can do it. And of course, from our side, research never stops. So next step is to maybe visualize what the eye cannot see yet. So this is probably how I would like to formulate it, because of course we are never finished with anything. So that's how research works. So stay tuned for more. And we're happy that the exhibition will be extended by another couple of months because we think it's a great exhibition, and Sarah Kenderdine is one of our also great friends here that we were happy to actually put an exhibit in her show. So let's hope for the best and see what the future brings.
Awesome. Thank you both very much again, and hopefully you'll come back to join us until the end of the exhibition one more time. And sure. I want to say thank you to everybody that actually joined us in today to watch the conversation, and wish you all again happy holidays from EPFL Pavilions, and see you next year.
Thanks for having us. Bye.
Thank you.
Bye, everyone.